So I don't see my presentation. Oh, yeah, it's not active. There you go. All right, so wait a minute. This is probably software engineering 1. Yes, it's software engineering 1. Let's go to operating systems. Forgot to switch folders. And we were in IO systems. All right. So here we go. And we have Timothy, or Tim, you go by Tim, right? With Android. So you ready to take over?
Yeah. I'm not doing the oxygen. I'm just doing the Android.
Okay, that's fine. Yeah, there's probably not enough specific to oxygen.
Yeah, that's what I was struggling about. Couldn't find a lot of information on it. Okay.
Okay.
Let's see here. Screen share. Okay. Can you all see my screen?
Yep.
Okay. So, for the devotion, I wanted to switch it up a bit. I know it's the last devotion that we're gonna have, but it's so it's not a lot of people did Bible verses, which is great. But I did the I want to talk about the serenity prayer. So I've been in circumstances in my life where I have done something wrong or thought I needed to fix something between people, and I didn't know what to do. So the serenity prayer is a petition to God asking for calmness and peace in all matters of life. Ask for strength and courage to alter the matters within our own control, and for acceptance in matters which cannot be changed. Ultimately, the prayer requests the ability to identify which circumstances are possible to change. This prayer is very applicable to most situations in life because God always knows best. So the prayer goes, God, grant me the serenity to accept things I cannot change, courage to change the things I can, and wisdom to know the difference. So this was written by a Dr. Reinhold Niebuhr in 1930s. Like I said, it's a petition to ask God for calmness, peace, strength, and courage in all aspects of life. And it is, while it's not in the Bible, it is definitely biblical. So 2 verses that talk about this are Proverbs 20:24. So it says, a person's steps are directed by the Lord. How then can anyone understand their own ways? So God knows, everything, and he's in control. So while we don't always know what's going on, especially like with the time, Corona times and stuff, we don't know what's going on, what's next, but God does, and we have to trust in him. And then also Matthew 16:3 says, in the morning, today will be stormy, but the sky is red and overcast. You will know how to interpret the appearance of the sky, but you cannot interpret the signs of the time. So we cannot change the weather, what comes our way, but we can ask God to help us along the way. So I've used this a lot, and it's very helpful when you're not sure what to do, or if you've wronged someone, if you should just leave it alone, or apologize or whatnot. So it's very it's been very helpful to me. So
yes, thank you, Tim. So that's a great message. I'm glad you brought that up, especially at this time, because you have classmates that are going through struggles with this COVID-19 thing, but other struggles as well. Do you mind? I'm going to jump in and share something, and then have you switch back in again.
Yeah, go ahead.
So, and while I'm doing that, feel free to comment on that thing. But I wanted to bring this up. So what Tim actually presented was a shortened version of it, and you see that commonly as the Serenity Prayer. But I wanted to bring up this full version of it because there's a lot of power in the rest of it that's generally not shown. So it says, God grant me the serenity to accept things I cannot change, the courage to change the things I can, and the wisdom to know the difference. Living one day at a time, enjoying one moment at a time, accepting hardship as a pathway to peace, taking as Jesus did, the sinful world as it is, not as I would have it. Trusting that you will make all things right if I surrender to your will, so that I may be reasonably happy in this life and supremely happy with you forever in the next. So, yes, I love what Timothy presented, but I think there's great value in the rest of that particular quote for that prayer. So, but yeah, I'm really glad you brought that up, Tim, because I know there's some students that need to hear that and reflect on this prayer. So that was an awesome devotion. So go ahead and take over the screen again, Tim.
Okay, yeah. No, I apologize. I didn't share the whole thing.
No, that's fine. That's fine. I just thought what you presented was important enough. Let's spend a little bit extra time on that.
Yeah. All right. You can see the screen.
Yeah.
Okay. All right. So overview. So Android is a mobile operating system based on a modified version of Linux, and it's mainly used for smartphones and tablets. It's developed by the Open Handset Alliance, led by Google, and there's, I believe, 84 other companies that are officially part of it. So the first beta version was the Android Software Development Kit was released in 2007, and the source code for Android is available under free and open source software licenses. So the history of Android. So it was founded in Palo Alto, California, in October 2003 by three young men: Andy Rubin, Rich Miner, four, Nick Sears, and Chris White. Actually, and it started out to be a company where they were it was for digital cameras, so they wanted to develop advanced operating system for digital cameras, but they struggled to get investors, and they actually were facing evictions from office space. So you hear a lot about people that were struggling, Bill Gates or other people that struggled initially to get going, but then obviously Android's huge now and caught on. So it finally started to catch on, and then Google bought it for at least $50 million in 2005. So that was a lot. That's a lot of money. So and then in 2007, the Open Handset Alliance was formed, and HTC, Motorola, and Samsung are some of the major companies that are part of that, with Google leading it. And as you most know, Android has seen numerous updates which have incrementally improved the operating system, adding new features and fixing bugs in previous releases. So here we have this is kind of cute. So every new release, they have like a little what is it? A fruit or vegetable, or some sort of food as their newest release. So and the API level is an integer value that uniquely identifies the framework API revision offered by a version of the Android platform in the bottom right corner, as you can see. And this picture is a bit old, but it's the current version is 10.0 now. It's not 6.0. So applications. So pre-installed apps, most people know, Gmail, you got your Google Maps, you have your Google Chrome, YouTube, Google Play Music, Google Play Movies and TV, and most apps are written using the Android SDK and Java, but it can be combined with C and C++, and this allows for better C++ support. So Go is also supported, but has a limited set of API. And then spring 2017, they announced that Kotlin would also be supported. So memory management. So this is extremely important because Android, as I stated earlier, is for mobile devices, and they need to conserve battery power as much as possible. So when things are running unnecessarily, it cuts down on battery life, which is one of the biggest things that they struggle with. So so when the memory is low, the system will begin invisibly and automatically closing inactive processes starting with those that have been inactive for the longest amount of time. So they had this it's called automatic adjustments that they have tried to stop or try to like secretly close and like try to make adjustments on its own to support and increase like battery life and all this stuff. But there's been some pushback actually, and there's been companies, Lifehacker was one of them, but there were some others that made articles and wrote about how it was doing more harm than good. They thought user would be was better at handling trying to close and stuff like whatnot. So, but yeah. And then your hardware, a deal is 2 gigabytes at least, past 7.1 update. And then with newer phones, obviously new hardware has been added. And the main hardware platform for Android is ARM and ARM v7 and v8. And 86 and 86 64-bit architectures are officially supported in later versions. So the newer ones. So and Android devices incorporate many optional hardware components, as most of you know. So video cameras, GPS, orientation sensors, dedicated gaming controls, accelerometers, gyroscopes, barometers, magnetometers, proximity sensors, pressure sensors, thermosensors, and touchscreens. So obviously, not all of these are required, but they do increase the overall performance of the phone. So, and that is it. So thank you. Any questions?
Oops, I'm muted. So how many of you have Android phones? Yeah, fair amount of you. Yeah, I think a lot of people that do development for phones like the API for Android over that of the iPhone. So it's interesting, the battle between the two major players. All right. Well, thank you, Tim. So I'm going to go ahead and share my screen again. So as usual, the administrative items, we have the Chapter 10 mass storage programming problem due tonight. And then Monday, May 4th, which is the first day of finals week, is the optional programming exercise. And unfortunately, the assignment was a little unclear. So what I'm looking for is not one of the exercises. So there's actually only one programming problem. So it says any of the programming problems in chapter 12. Well, it turns out that 12.21 is the only programming problem in chapter 12. So that's the one that I'm looking for. It has you using symbolic links and working with symbolic links and things like that, and looking to see how the file system works and is implemented in various systems, or in Linux, I believe. So that's the assignment. Now, I did have one student that submitted one of the exercises already. So what I did was I gave that student partial credit, but if they would like to go back and do 1221, they can get the full points for that extra credit programming problem. So, and then the other thing is Tuesday, May 5th is the remainder of the quizzes, chapters 10 through 14. So I put that right at the end, right before our final, which our final is on Wednesday. And since it's online, it will be Wednesday by midnight if you choose to take the final. But then remember my offer that if you have no zeros for any of the assignments, that you're eligible to decide to not take the final without any penalties. The one caveat is if you're a senior on the exempt list, you can do that even with zeros and decide you want to do it. So that's for the graduating seniors on the exempt list. But make sure you verify you're on the exempt list before you take that option. And also, you may want to check in with me to make sure that I agree that you don't have any zeros for your grades on any of your assignments before deciding to opt out of the final. The other thing is that you are allowed to go back and do quizzes or assignments late, turn them in late for partial credit, but it'll also qualify you to, if you fill in all of those, to go ahead and decide to skip the final. And for those of you wondering, the final will be based on primarily the study guide. So there's 2 study guides, one for the midterm that you took, and the second study guide is actually a midterm that never happened because of the change in schedule of semester. So it's primarily based on that information, and the final will be open book and open note, but please don't use any web references or Google searching. But again, the better you know the material, the easier time you will have to complete the final in the allotted time. So, some studying would probably be in order, even though it's open note and open book. So any questions on the administrative items before I proceed?
Do we have to use C for the programming for all of the projects?
No. If it doesn't explicitly say to use C or C++, then no. You can use other languages if it doesn't explicitly state that you have to use C.
Okay.
So there are some that specifically state that you should be doing it in C in Linux, etc. But other than that, no. So one example of that is the Dining Philosophers actually does state, does walk you through the exercise in C. So that would be one of them that I would expect in C, would be one example. But there's others that explicitly stated. But if it doesn't state, like some of the threading programs, you can do that in Java. It doesn't have to be in C. That would be one example of a case where it doesn't matter. But yeah. So, and shoot me a message if you're unclear whether the assignment specifies the use of a particular language or operating system, and/or, I guess. All right. So let's move on back to I/O systems. And again, fortunately for operating systems, we kind of fly through the material because there is so much of it. But please interrupt me if you're not catching something, because I will tend to go pretty fast. So stop me if there's something that you don't understand or need explained. So we talked about before the interrupt vectors as being a more efficient way for tasks where there's a lot of information being transmitted versus polling. We looked at the interrupt vector for an Intel Pentium as an example. The other places that interrupts are used are for exceptions. If something happens that was unexpected, it can terminate a processor, etc., and an interrupt can be generated. Page fault is another example where we talked about virtual memory, where you have page faults when area of memory is being accessed in the virtual memory logical space that doesn't actually fit and is not currently in a physical page, then you'll get a fault, and that will be driven by an interrupt. You can also have various calls that can trap to a trigger kernel, to trigger a kernel to execute a certain request. So certain system calls may result in an interrupt. And then You have an extra level of complexity with multiple CPUs, where now you have multiple CPUs that can generate interrupts and processes, so that there's an extra level of complication involved with interrupts and who do you interrupt, and is there shared resources that somehow have to be protected from interrupts on other processors. And again, it's used for time-sensitive processing where it happen quick and frequent and fast. And key thing to remember there is that an interrupt service routine, therefore, has to be short and concise and very limited in what is actually executed in the interrupt. So generally, it will be transfer of information into a certain place of memory or something along that lines, and then there'll be another process outside of the interrupt that will actually do most of the work, so that you don't hold up other interrupts from occurring and processing. Direct memory access was another example, and this is where you're bypassing the CPU to transfer information directly between the I/O device and memory. And so what happens is you put in your request, the disk and the takes over and controls the access and transfer itself by stealing cycles from the CPU to the memory, but not involving the CPU involved at all. So this frees up the CPU to do other things. But the key thing here is that eventually the CPU process needs to be notified that the transfer actually has been completed. And that's when an interrupt will be generated, is when the operation has been complete. So keep in mind that the DMA controller can steal memory access cycles from the CPU, allowing transfer of things to and from memory without keeping the CPU involved. I think we've discussed this in earlier chapters, but that's a key concept. That is the purpose of the direct memory access, is transferring things between generally the hard drive, but the mass storage device and memory without involving the CPU, leaving the CPU to do other things. So this is a diagram for your text, which outlines the 6 steps that are involved in performing a DMA transfer. You can see here the flow chart and certainly read that in text. I'm not going to go through it in great detail, but having said that, there is a set of concrete things that need to happen to actually initiate and then notify that the process that the DMA transfer has succeeded. So this is a pictorial diagram with the steps. So the application interface to the I/O is generally encapsulated in generic classes or abstracted classes to abstract the complexity of the device away from the application. So we talked about how that is accomplished through a device driver that hides those details and provides that uniform interface to the application programs and system programs of the operating system. There's also there was in the text, they also talk about how there's standard drivers for generic type devices, and so there are established protocols for each of these different types of devices that makes the job a little bit easier, but there will be slight differences in the device drivers for the nuances of the particular hardware that you're interfacing to for I/O. Each operating system has its own I/O system structure and a device driver framework, and that's why when you, for instance, buy a printer or something, you typically will have to have different device drivers for different operating systems, Linux versus Windows, for instance, or a Mac device driver for a particular device. The devices vary in many different dimensions. So here are some examples. We have character streams versus blocks, which is blocks of data. Keep in mind that a character stream is actually 1 byte at a time. So it's usually used for a fairly slow access device, like a keyboard, for instance, or blocks are larger amounts of information. We have sequential or random access. So are you progressing through the data sequentially, like in a magnetic tape drive, or random access like solid state drive or a magnetic hard drive would be examples of where you want random access. And then we have synchronous or asynchronous communication between the process and the device, but you could also have mixtures where you're allowed to do either one. So both are supported. So synchronous is when you put in your request and then the process waits for that operation to complete and doesn't do anything but just wait for the operation to complete. And then asynchronous is where you can put a request in and then get interrupted or notified that the request has been fulfilled. And in the meantime, you can go off and do something else in that process. We have shareable devices or dedicated, that they're dedicated to something or are shared across multiple processes or multiple things, operations in the operating system. Various speeds, there's different levels of speed that can access, an obvious example that many people are seeing now is the speed up in solid state drives by using non-volatile memory, that the speed of operation has increased considerably over that of a magnetic drive. And then we have things that operate at internet speeds, memory access speeds. So there is a wide range of different speeds that the devices that we're doing input-output with can operate at, and we'll have different design decisions for how to best access them. And then we have, in the example of files, we see this a lot. We can have read-write mode, read-only, where you're only allowed to read, or write-only, where you're only able to write. And so examples of that would be writing to a CD or DVD, although we do have erasable CDs and DVDs, but you have the write once version where you can only write. Let's see, wait a minute, is that right? Let's see, write only. No, because you actually are reading from it. So that's a bad example, but you could have things where you're writing to some source and never expecting to read to it from it. So that would be the write-only case. I'm escaping me at the moment to think of a good example for that, but you can imagine that is one of the permutations that's available for a device. So here's again a diagram for your text about a layer diagram about how to access it. We have the kernel I/O system, and then the device drivers, and then we have the hardware and the hardware interfaces like SCSI and your keyboard devices, and then ultimately down to the devices. So you can see that it's typical to have a layered approach to accessing I/O devices. So there are various characteristics. We talked about that, block versus I/O, memory mapped or over a network. So there are various subtleties that are handled by the device drivers, like we said. For direct manipulation of I/O devices, Unix uses IOCTL call to send arbitrary bits to a device control register and a device data register. So that would be a very low level call and generally not used unless you are probably writing device driver to control the individual bits of registers or to memory in the case of memory mapped I/O devices. Probably won't quiz you or hold you too much to this information. It's pretty straightforward though. I talked about block and character devices. Generally, character devices are things like keyboards, mice, and serial ports, where serial ports is a lot of data going across a communication channel, but it is quite slow compared to contemporary accesses like Ethernet or again DMA or raw access to a file system. And again, we talked about raw communication as being common for swap files for virtual memory, and the other place that generally is done is in databases, because database knows a lot about the information and how it's stored and can optimize access to the database to improve the database performance. So those are areas where direct raw access is common. So I talked a little bit about this already, but network devices are common, and they can vary between block and character, or somewhere in between, based on the speed. And then so Linux, Unix, and Windows and many others provide a socket interface, and you're probably familiar with sockets and ports associated with different sockets. And we talked about how internet addresses is the address plus the port is the internet address. And so that would be the way you access network approaches. You can also use socket within the same machine as well. It doesn't necessarily mean that you're going out across the network to another computer, but that is a common use case for sockets. And then they talked about various approaches that can be taken. We have pipes, first in, first out queues, streams. So you see this a lot in Java, streaming model. Queues, and then mailboxes. So this is message passing, would use a mailbox scheme. So blocking and non-blocking, key thing to keep in mind here, we talked about this, but the execution of the application is actually suspended when you're blocking, and then a blocking system call is used. So that's a synchronous method. And then non-blocking would be where you actually can put in out your request and then move on to read the data. So it talks about select to find if data is ready, and then you read, or write to the transfer. So you do a select statement and are then notified when the information is available. And then asynchronous is a little bit more complicated and difficult to use, because you have to take care of the asynchronous nature and the multi-threaded nature and the fact that timing and race conditions and those kinds of things have to be taken into account. And so that, but with that extra complexity and the extra work, you then get better, you can get much better performance. So, but use it sparingly, because there is some complication in going to an asynchronous model. So again, the execution of the application is suspended when a blocking system call is issued versus a non-blocking. So there's also a discussion in your in the text regarding various techniques that are used in the kernel I/O systems. Some techniques for scheduling, buffering, which is a mechanism for coping between the speed mismatches between the I/O device and the CPU and memory and other devices. So you can use buffers in between to smooth out those differences in speed and handle those differences in speed gracefully. So this talks about some of those varying techniques that can be used. We won't go into great detail about that, but please be aware that those are options or things to consider if you were ever to have to write your own device driver. For instance, if you're developing your own hardware, then yeah, you'd have to create a device driver. Here is just sort of a spectrum of speeds. You can see a keyboard is way in the very slow. Notice that this is exponential graph here or chart. And so we have keyboard, mouse, and modem. Hard disk, FireWire is up here, SCSI, gigabit, Ethernet, serial ATA, and up. And we have the system bus, which is the CPU bus. And then we have PCI Express, but Hypertransport I actually haven't looked too much at, but that's be interesting to look at. But anyway, you can see that there's a great range of speeds of devices and their I/O speeds that they're capable of handling. Other aspects of the kernel I/O system, we talked about buffering and caching is very similar, but the caching aspects is that you try to save information in the faster memory and in your buffering, and you're always trying to guess what information is going to be needed, much like virtual memory when you're trying to save, prevent page faults from occurring. Similar thing with the caching. And then spooling, you can think of that is generally talked about in conjunction with printing, a spooling device that will keep a queue of items that are being spooled to a device. And then device reservations, which is providing exclusive access to a device for a certain time. Again, here it says, watch out for deadlocks, because when you have exclusive allocation and they're able to grab other resources that in the same time, that there may be a conflict between two resources that they're each holding the piece that the other one wants and trying to get access to the other, and neither of them are willing to give it up. It can certainly end up in a deadlock situation. Key things here is with I/O operations is error handling is important, because there is no foolproof I/O transfer. There's always need to be able to recover from read and write errors. There are various examples there. We talked about the text talks about Solaris systems for error handling, and then we talked about error correcting codes in memory and on disks. So all kinds of different schemes have been reported, but keep in mind that most operating systems have some system of maintaining error logs so that you can go back and do a retrospective and figure out what went wrong or discover something has gone wrong. And when you're writing application code, you will need to periodically check the system logs and say, hey, wait a minute, something's going on here. I'm not quite sure what's happening. And a good place to look would be in the system error logs to see if there was some error associated with the operation you were doing. The most recent case where I was perusing the system logs a lot was there was a database corruption error on this system that we were using that was popping up periodically, and I was working on backup and recovery schemes. And an important place to figure out what the cause of the error was so that you can recover was in the error logs. So we actually had, as part of our code, parsing through some of the error logs and discovering what went wrong so that we could mitigate some of the problems that were happening in the database in terms of corruption. I/O protection. This is just making sure that processes that are trying to access I/O are privileged and they're not rogue processes, either purposely or accidentally. You always want to be aware that sometimes people are writing code and they're not really doing things correctly. And so, again, the outer levels So the kernel will be trusted, but as you go up to the application levels, that would have higher degrees of protections against them, and you would rely on the trap down into the kernel for doing the operations, because that is your trusted code that has been well tested and accepted as trustworthy in order to access some of these I/O. So generally, we're talking about a system call trapping down into the kernel. Here are some of the kernel data structures. Again, I'm not going to talk too much about it, but you've all come across this concept of dirty, which means that the information has been changed in the buffer since it's last been used. We saw this with virtual memory as an example. And then there's lots of object-oriented methods that are being used, message passing, all kinds of different techniques that can be used for the implementation of I/O. So lots of different unique techniques. But again, we're not going to go too much in detail about that because there is such a broad range of things that are done. Power management. So this is not strictly an I/O issue, but it is I/O related, that you need to access information about the battery life of the computer, especially laptops. There's also cases where there's monitoring of your CPU to make sure that it's not getting too hot. And so OSs can generally be involved in helping with that. And then certainly mobile computing has put power management as a key component of what the operating system does. And certainly we all know that various releases of either Android or iOS operating systems have been critically evaluated based on how well they handle power management, because it's one of the things that is a huge selling point, is how well and how long can you last on a particular charge. So it's become a very important aspect in mobile computing. So yes, I think that would be a huge takeaway, is the fact that mobile computing has really upped the game in terms of techniques for power management, that it's become critical in that realm. All right, so that is it for I/O systems. Any questions about that? Again, I can't emphasize enough, I am going quickly, and I know I'm going quickly, so interrupt me if something doesn't make sense to you. Chapter 14 is the last chapter we're going to cover, and that's protection. And so we'll go into that, but certainly we've seen this in terms of file interface, about protection models for files, and that's one of the most common things that we can think of as access to particular files. So in protection models, it's usually a collection of objects, hardware or software. And so certainly files are a common object that we try to protect with a protection model, but you can also think of ports in terms of protecting ports and firewalls, and that for internet traffic. So lots of different realms in the protection world. And certainly you will see a lot of this in Dr. Gowing's classes on computer security. So each object has a unique name. Again, you need to be able to identify it uniquely. And a well-defined set of operations. What are the operations we can perform? And if we know what kind of operations we can perform, then we can also set protection levels on who is allowed to do what operations. So the protection problem is, in a nutshell, ensuring that each object is accessed correctly and only by those processes that are allowed to do so. So you can access what you have privilege to do, so you can only do those operations, and only the processes that are allowed to do that are allowed to do so. Principles of the guiding principle is principle of least privilege. So programs, users, and systems should be given enough privilege to perform the tasks that they're allocated to do and no more. So again, going down to the lower levels of your operating system, the kernel is given quite a lot of leadway, but system programs, on the other hand, although they're given privileges, are not given the same privileges as the kernel. So you want to have the least amount of privilege given to whatever process is being used to accomplish this task. And that's why we have to go in Linux, where we talk about sudo, or bumping up our priority when we need to do a particular operation as an administrator. But then as soon as you're done with that administrative stuff, where you are on the top of your game and thinking really closely about everything you do, because you know you can do damage to the system in system mode, you would then generally leave that root or privilege mode in order to do your normal things, so that you don't, in your day-to-day operations, accidentally do some damage to the system. We talked here, and this I already referred to, is we have this concept of privilege escalation and domain switching. So domains are groups of generally users, but some group of things that are allowed to have access in this domain, and you can quickly switch between those domains as you're doing your tasks in terms of what you need to know and what you should have access to. We have different levels of granularity. You could have rough grain privileges, which are easier and simpler, but there's larger chunks, so that you can't actually limit as closely to this least privilege concept, because it's more rough grain. Or you could have fine grain management, which is more complex but more protective. Examples of this for files are access control lists or role-based access control. Those are some examples of where you would have a little bit more finer control. But again, it comes with more complexity. A domain can be a user, a process, or a procedure. Generally, the most common is this first one. User is usually the most common form of domain that's used. And so generally, a process will be owned by a user, and it will adopt and use the privileges owned by that user for that particular process, unless there's a mechanism that you use for escalation. So again, this concept here of escalation. So that pretty much takes us to the 5-minute warning. Are there any questions before I let you go? Because I know I ran over last time, so I definitely don't want to run over two lectures in a row. Oh, one thing I didn't discuss is there should be an email going out for course evaluation, and actually there's special provisions for the fact that we went online. But please provide any feedback you can by doing the course evaluations, because that helps the instructors, not only myself, but the other instructors as well, to fine-tune their courses. And our goal is definitely to have as much learning and of information of our topics that we can portray as possible. So we're always looking for better ways to present things. And I know I'm still being a fairly new professor, I'm always working out the schedule and trying to figure out the timing of how the course should proceed to give the appropriate amount of depth versus breadth of the topic. So there's a lot of breadth in a lot of these topics, but I want to have that balance where there's enough opportunity to go into depth that you have a deeper understanding of the information, not just superficial, but also have some exposure to the breadth of the topic in mind. So that's one of the things I'm always struggling is the timing of the course. So with that being said, if there are no questions, I'm going to stop the recording and you're dismissed.